Before we start talking about how to build phylogenetic trees, we need to get some things in order about terminology and about the graphical representation of trees. So let me just talk a bit about that. In evolutionary biology, when we talk about phylogenetic trees, we typically represent them in this graphical manner. So a tree is built from nodes, the little white circles that we have on this plot, and branches connecting the nodes. The nodes can be terminal, meaning they sit at the end of a branch. We then also refer to them as leaves, and these will typically correspond to present-day living organisms. Nodes can also be internal, meaning they sit inside the tree, and they then correspond to what we call hypothetical ancestors. So for instance, this internal node corresponds to the ancestor of these two present-day organisms. The node at the bottom of the tree, the most ancient internal node, is called the root. This is the ancestor of every single individual, every single organism in the tree. When we look at trees, we typically think of them in this shape that I've shown at the top of this slide. This is what we call a fully resolved or bifurcating tree. This tree, for every internal node, it has two branches going out. The reason that we typically think of evolutionary trees looking like that is that that's how evolution typically proceeds. We have some population of animals. That population is perhaps split into two by some geographical barrier like a mountain range or a river. And these two separate populations then start acquiring mutations, either as a result of genetic drift or as a result of adaptation to the new environment, to the point where the two populations can no longer interbreed. And at that point, we will have two separate species. So typically, species are formed by one original population splitting into two, and these two new populations then form a new species. So bifurcation is how speciation typically proceeds. Incidentally, the bonobo and the chimpanzee is one recent example of this, where we have one population on the north of the Congo River and the other population on the south, clearly originating from some original chimpanzee-like ancestor, being split by the Congo River and then acquiring mutations to the point where there are now two separate species. However, sometimes we will see a tree that has more than two branches going out from an internal node, like the tree we have at the bottom here. We call such a phenomenon a polytomy, and we say that the tree is partially resolved. We say it's partially resolved because typically this is not a reflection of the actual biology. It's not typically the case that we have three species forming at one instant in time from one original species. Rather, these trees, these polytomies, are mostly a result of us not having enough data to resolve whether the split occurred on that branch or that branch. But we will see them now and again. There are cases of explosive radiative speciation where an animal moves into an entirely a place where there's a range of ecological niches that are not used, and we can then very rapidly get adaptation to all of these niches. But on the whole, polytomies are the result of lacking data, not of actual biology. Another term that's important is the idea of a monophyletic group. A monophyletic group, or what we also call a clade, is a group of organisms that include all descendants of their common ancestor. So in this case, the common ancestor is the internal node here, and the group includes both descendants. Monophyletic groups are interesting because all the members of such a group, they will have a number of shared characters, and they are typically those that they have derived from their ancestor. So all the features, for instance, if you're a bird, then you have a lot of things in common with other birds, feathers, a beak, etc., etc. And if you find a new bird, you can immediately infer that it will share all of those derived characters also. Non-monophyletic groups, or as in this case, what we call a paraphyletic group, are less interesting and are not used much. Although I should mention that the classical definition of what a reptile is, which excludes the group of birds, is actually a paraphyletic group. For reptiles to be a real clade, a monophyletic group, it should include birds under that heading. And there are some systems where you do include birds, in fact. In addition to the terminology, there's an important point I want to make about representation. So it's important to realize that the thing we're interested in a phylogenetic tree is the branching pattern, or what we call the topology. That's the interesting information that we're after. If you look at the tree on the extreme left of the slide, you can see that we have these 5 species. It have a branching pattern where we have A closely related to B, less closely related to C, still less closely related to D, and the farthest related from E. You can see that every time we have to go back an ancestral step, we become less and less related to it. So if you have to go back just one step, one ancestor level, then you're like sisters. If you have to go back 2 levels, then you're like cousins, etc., etc. So the further back you have to go, the less related you are to those other organisms. Anyway, if you take the entire tree on the left and rotate it around its basal branch, if you mirror it, then you get the second tree. You can probably easily see it's the same tree topology. We still have A closely related to B, less closely related to C, still less closely related to D, and the furthest away from E. So these 2 trees are exactly the same, even though they look different. However, it becomes more tricky when you start doing the same inside the tree. So in fact, like we just rotated the entire tree, we could also rotate just a subtree inside. So if you take the subtree consisting of A, B, C, and D and rotate that around this internal branch, we will get the final tree on the slide. This looks maybe quite a bit different from the original tree, but it is in fact entirely the same tree topology. We have A closely related to B, less closely related to C, still less closely related to D, and the furthest away from E. So entirely the same tree topology that we saw before. This is sometimes important to keep in mind when you look at a tree. You should not be fooled by whether 2 labels are adjacent. At the top here, what is more interesting is the branching pattern. How far do you have to go back before you find their common ancestor? That's what's telling you how closely related they are. Another aspect of representation of trees that's important and that we will talk about in the course is that of rootedness versus unrootedness. So a rooted tree, again, is the sort of tree that we're used to look at and to think of in evolutionary terms. A rooted tree, not surprisingly, has a root, and the branches then emanate in a direction from that. In a rooted tree, the root is the oldest point in the tree, and internal nodes in the tree can be ordered in terms of older or younger. So for instance, the node that's here is older than the internal node that's out here. And on the whole, evolutionary time proceeds in the direction from the root towards the leaves, as indicated by the arrow. It's important to realize that in a rooted tree, the other dimension in the tree, the vertical dimension here, does not mean anything in terms of genetic distance. It's just there to spread out the leaves. Only the horizontal orientation in this particular rooted tree carries information about genetic distance. So I should maybe mention that branch lengths, the longer the branch, the more mutations, the more changes have occurred on that branch. Unrooted trees are are something that maybe some people have not seen or that they haven't seen that often, and they look like this. This is just the same tree as before, but without the root placed. Okay, this in fact is what most phylogenetic reconstruction methods give us. In most cases where we use a DNA dataset as the basis for reconstructing a phylogenetic tree, there's not information in the dataset about where the root is, and the result is instead an unrooted tree like the one I've shown you here. We then have to use external information to infer where the root is. There's something called outgroup rooting that we will return to, for instance. It's important to realize that how to interpret an evolutionary history depends entirely on where the root is. If the root is at some branch, then all of these other forms a clade. If it's on the other branch, then these do not form a clade. So what forms a clade, what forms a monophyletic group or not, will depend on where the root is, and therefore your evolutionary interpretation will also depend a lot on where the root is.